Does anybody have questions before we get started about your graphs? Yeah? Yeah, after you download the package. So you have to download and install it. You do that just once. And then once you've done it, it's like the violin plot if you use the violin plot. As long as you've done it once, then it's there. Do you have a Mac? So there's one of the options in the GUI is to install package, not load, install. And then you get a list of all the packages and look for capital R, capital C, color, capital B for Brewer. And then once it's installed, you're fine. Yeah? It depends on what format it's in. Are you using Many Eyes? So it's probably a TXT file that's tab delimited. So you can use either read.delim, D-E-L-I-M, or you can do read.table. If you use read.table, then you have.
What I was referring to was like after you've downloaded the original data and then you go online and then you find additional data.
Oh, additional data. Depends on the particular circumstance as to what you can open like a text editor and just type it in.
We can edit our data outside of R.
Yeah, yeah. I mean, you can do a lot within R, but that's beyond the scope of this class. So if it's a small amount of data, you can type it right into R as, x equals C for the concat function, paren, then the values separated by commas. You can do that. That's fine with me. Right. If it's a lot of data, you're not going to want to have to do that. But are there any other questions before we get started about the homework 2, which is now due Wednesday at midnight? No? So today we're going to talk about numerical summaries. And we've already talked about them once. I think it was, oops. This is bad. When this happens at the start of class, then they lose the signal. And the screen goes blank. I don't know if you've watched any of the things of the lectures, but that's what happens. Okay, so we're going to talk about numerical summaries today. We already spent some time on it, I think, a week or 2 weeks ago. And this should mostly be review aside from 2 new ideas. But this is going to be a way to summarize numerical summaries. And let's see if we can get this going. There we go. Okay, we're going to start with the mean or the average. I use those two interchangeably. Here's a set of data that you're very familiar with. I have only put the first 4 values, 60 inches, 62 inches, 58 inches, 61, ... 70 inches. I'm missing an inch on that one. The average height for a mother is when we add up all of the values across all of the mothers and divide by the total number. We have 1,214 mothers in our study that have heights that are reported, and the average of those values is 64 inches. Now we're going to do a little bit of notation. This is the first time that we've seen notation in this class, but it will be helpful for us when we get to the correlation coefficient, which will give you the mathematical notation for that. So we are going to abstract the notion of the height for the first mother in the study and say that that's x sub 1. Then x sub 2 is the height of the second mother in the study. X sub 3, the height of the third mother, ... up to x sub 1,214 is the height of the 1,214th mother in the study. The average then we call x bar. That's just a special symbol. And it's essentially the exact same thing as what we did on the previous slide. we add up all of the values for the heights, x1 plus x2 plus x3 plus x4, dot, 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 up to x1214, and divide by the total number of them. Down here is a summation notation, which is now covered up by this symbol. There we go. The big sigma stands for summation, and we sum from I equals 1, that's the starting point, to 1,214, and we're summing xi. So that means we run the value I over all those different possibilities, starting at 1. So for I equals 1, we get x1. And then we add it to I equals 2, x2, 3, 4, up to 1214. I'm hoping all of you are familiar with this because calculus is a prerequisite for this class, so this should look really easy and very familiar. Okay. So what are some of the properties of the mean? The mean is the balance point of the density plot. And by what I mean by that is that if we could print out the density plot on cardboard, something like that, and cut out the shape, and then think of it as like a seesaw, and where would we have to put the fulcrum so that it balanced? That's what I mean by the balance point, sort of a center of gravity. So the mean is the balance point of a density plot. The mean is also, because it's this sort of balance point, means that it's very sensitive to large values, either large positive values or very small values, or just large values or extremely small values. And it's also sensitive to having a large or long tail. One other property of the mean is that, and this is sort of calculus speak, it's that if you have a linear transformation of your data, then you have a linear transformation of the mean. Let's put that in normal speak. If I were to, for example, take the height of those mothers in inches and convert it to centimeters, to do that I would multiply them all by 2.54 centimeters per inch. That would be, I'm multiplying all the values, the 60 inches, the 62 inches, the 70 inches, by 2.54 centimeters per inch. That changes my units, and the new mean is just 2.54 times my old mean. A different example, if I had measured temperatures in Fahrenheit, and I wanted to convert it to Celsius, I would then, does anybody know the conversion? Yes? You subtract 32, and then you multiply by 5/9. And so it's this similar kind of thing. That's the same kind of transformation, which says that then if we have an average temperature in Fahrenheit, we know how to do the conversion using this same technique. Okay, so here's the mother's height density plot. Question to you, where's the balance point? So throw out some ideas, some guesses. Yes? So the balance point's at the bottom, along 55 to 70. So what do you mean by the top left?
I mean, like, it would be straight down.
Is it 60?
Like, yeah, 60.
65?
Maybe.
62?
Yeah,
63? Okay. 62 to 64? Yes? Can anybody narrow it down a little bit? Yes?
Where the 64 is like up?
It's where the 60, and you know that because I've already told you the mean. Yeah, it's actually at 64. But this is roughly symmetric, and so it should be roughly in the center. It's not quite symmetric, and that's why you're trying to hedge saying exactly where it is. Here's my picture. That's the balance point. So I've drawn a little balance line, and I put a little fulcrum to show you where this thing's supposed to balance. So it doesn't teeter and flop one way or the other. It stays balanced. Okay, let me give you a little harder one. Here's data that come from collecting water in a creek and measuring the amount of fecal coliform counting. And this is a really unusual distribution. And I'm asking you what's the balance point, and I've given you 3 options. So the first option, I'm not even going to tell you what the actual numeric value is. Yes? You think it's the middle one? Yes? What value do you think that might be, roughly? 1,000. It is exactly 1,000. The one on the left is 400, and the one on the right is 1,800. And in fact, it is 1,000. That's the balance point. So notice how those very large values around 6,000 are pulling the mean out so that you can still balance. If I go back to this and, there's my question. In this particular case, where's the median? So the median, remember, is where half of the values are below and half are above. Median is talking about the area under the density plot, because area corresponds to proportion or percentage. So what's the point where half of the area of this density curve is to the left and half is to the right? Is it going to be about 1,000? Yes? And how much smaller do you think? About 200 or 300? That's way, this other red one is 400. So is it to the left of that? It's even smaller? Actually, it is 400. So the first red triangle I put up there is actually the median, and the second one's the mean, and the last one's just an extra point. Standard deviation is a way of measuring roughly what's the typical or average distance that you might find the values from the mean. So standard deviation goes hand in hand with the mean. Again, if we have our same mothers, our 1,214 mothers, and their heights, now we know their average is 64. What we do with them is we take each height, like 60 inches, we subtract the mean, that's the deviation, and we square it. Then we add it to the next deviation squared, 62 minus 64 squared. We add it to the next deviation squared, 58 minus 64 squared. We get all of those sums of squared deviations. Then we divide by the total number and take the square root. And that gives us 2.5 inches in this particular case. My question to you is, why are the units in inches? Does that make sense that the units are still in inches? Yes, if I'm thinking about how far away I might find a typical observation, I would like those units to be in inches, because that's what I'm measuring height in. If we take a look at the actual computation, mother's height's in inches, and then I square it, so it becomes inches squared, and I'm adding them all up and averaging them, so it's still inches squared. But then at the end, I take the square root, and so it's inches. So if we follow our units through the computation, we see that, yes, it makes sense that it's inches. Mathematically, putting in the notation, again, we bring back our x1 to represent the height in inches of the first mother in the study, x2, etc. Now we've got x bar, which is our mean. Again, our sigma notation says sum from I equals 1 up to 1214. Now I've got my xi is x1 would be the first mother. Subtract the x bar, so that's my deviation. Square it, sum them up, and divide by the total number and take the square root. So that's how we represent it in much more compact form, and when we don't want to write out all 1,214 numbers. Another name for the SD is the root mean square deviation. And what's nice about that name, I like that name because it tells you exactly how to compute it. So in a sense, you look at that word in reverse. Deviation says, okay, find the deviation of each value from the mean. Square, square it. Mean, take the average of all of them. Root, take the square root of it. So if you can remember that alternative name, root mean square deviation, you understand what's going on in the computation of the SD. Fortunately for us, R does all of those computations really easily. You just call the SD function and it computes the SD for you. Okay, some properties of the SD. So we've already mentioned how the SD measures the distance from the average, and it says what's the typical uh, what's a typical distance of my data values from the average? And for lots of distributions, the one SD away from the mean will get you a lot of the data. For the normal or the bell-shaped curve, so roughly 68% of the data will be within 1 SD of the mean, and 95% will be within 2 SDs of the mean. What I mean by that is if I'm standing here at the mean and I look in one direction, 2 SDs away, and the other 2 SDs away, I'll see about 95% of my data. And if I only look 1 SD away, I'll see about 68% of my data. Just like the mean is very sensitive to large values, which we saw with the pollution data, the SD is also sensitive to outliers because it's also an average. In fact, it's in some ways, well, I'll leave it at that. Linear transformations. If I take my data and I multiply it by something and I add on something, so I multiply it by some value B, I add on A, how does the SD change? So I've got the answer there already, but let's think about what it means. What the SD means is how far away are my typical values. So if I take my distribution and all my values, and if I add a particular number to them all, that essentially does a shift to everything. Okay? If I multiply them all by a factor like 2, that stretches them all out. What was the highest value is now 2 times as far away. What was the smallest value is now 2 times as far away. And you were going to say? Oh, yeah. Yes, the reason? You're answering my question?
Yeah, no, the reason that A is not part of the US is because when you're shifting everything, that doesn't change the standard. Like, it's not going to change, like,
The distance, that's right, from each other. So, good. When you add A, that just shifts all the values, and it doesn't change how far away they are from each other. Therefore, A does not appear in the SD calculation. You could go back to the actual formula and put in the A plus B times xi and A plus B times x bar, and you can see automatically when you do that subtraction, the A's are going to go away. The B can pull out, become squared, and then square rooted. So that's why its absolute value is because it becomes squared and then square rooted. But the other thing is it's measuring distance. Distance is always positive, and it makes sense if you're stretching it by 2 or negative 2. Negative 2 is just also stretching it by 2, but flipping them around. And so the distance is then changing by a factor of 2. Another idea is converting data into standard units. What we mean by that is we subtract the mean and divide by the SD. And those are our new values in standard units. I have 3 questions for you. What's the mean of these new values? What's the SD of these new values? And what are the units in these new values? So we could go and actually go back and do all the calculations, or you can possibly guess from even the name of standard units what the answer might be to this question. What's the new mean of these values? Yes? It would be 0. And we can think of that as that's a linear transformation, just like before. I can look at B as 1 over the SD, and as x, and as A as minus x bar over the SD, and plug it back into my formula. But the other way to think about it, and then I'll derive that, in fact, it is 0. But the other way to think about it is I have taken all my data, and I've shifted it by x bar over the SD, right? And then I've scaled all my data by dividing by the SD. And so I've shifted it so the center's now 0, and the spread is going to be 1. Because remember what happens to the SD if I back up? If I have a factor times all of my observations, that factor just then gets comes out and is multiplied by the SD. So I've got a factor which is dividing by the SD. So my new SD is going to be the SD, my old SD divided by the SD, which is 1. So My new mean is 0 and my new SD is 1. What are the units of these values, of these new values? Think in terms of height. If the xi's are in inches, the x bar is in inches, the SD is in inches, and I'm dividing. So it's unitless. That's why it's called standard units. So when I do this conversion, my new mean 0, my new SD is 1, and I have no units. So the mean and the SD you'll see all the time when you're reading the news or looking at technical reports. Percentiles and quantiles don't appear as much, although they should probably be used more than they are, especially when we've got distributions that have long tails and outliers. We've defined this already as the pth percentile is the data value at which p% of the data are less than it, and 100 minus p% is greater than it. A few examples that we should all know by heart is that the median is the 50th percentile. Half the data is less, at least half of the data are less, and at least half of the data are greater than it. The upper quartile is the 75th percentile, meaning 3/4 of the data are less than or equal to it, and 1/4 greater than or equal to it. The lower quartile is the 25th percentile. When we are reporting medians rather than means, we do not use the SD, because the SD is a measure about distance from the mean. Instead, we use the inner quartile range, which is the 75th percentile minus the 25th percentile. Be careful not to use it in the same way that you use an SD. This tells you how far away the upper quartile and the lower quartile are. So if it says that roughly half of your, or exactly half of your data are within this, whatever this distance is, this IQR of each other. So it's not relative to the median. Couple properties of percentiles. When the data has some outliers or some really long tail, remember the median's based on the ordering of the observations. So if I tack on some really large values, or if I pull them out, that's not changing where the middle is. And so the median is quite robust against large values as outliers or a really long tail. For all distributions, half the data values are within the IQR of each other. That's what I just said when we were looking at the previous slide. What happens when we make a linear transformation of our data? So let's just think about it when b is positive. So I'm shifting my data, or I'm rescaling my data. Does that change the order of the observations? No, so the median should still be the old median, but now where it's relocated. And so it'll be a plus b times the new median, or times the old median. All right, I've now pulled 7 questions about means, SDs, medians, and inner quartile ranges and percentiles from this fantastic book called Statistics by Friedman, Pisani, and Purvis. These are all people who at one point were in the statistics department here at Berkeley. This is one of the most, many of the lower division stat classes use this textbook. They've got fantastic questions that really make you think. And I have pulled 7 of them as a way for us to review. I'm going to give you, we're going to time it. We'll give you each 30 seconds for each question to think about it, and then we'll see what kinds of answers you have for them. First question. Each of the following lists has an average of 50. For which one is the spread of the numbers around the average biggest and smallest? I thought, why don't we actually put a timer on? Let's see. Do you already know the answer? My timer doesn't go below a minute, so. You've had 30 seconds. Can we, we've had more than 30 seconds. Can you give me an answer? Or at least rule out one. Or give me an observation. Yes? You think, let's just give me one of them. Which do you think is the biggest one? Number 3. You think 3 has the biggest average, and why? Because if they each have the same number of values, right? And for number 3, 98, 99, and 100 are all really large. Okay, time's up. 98, 99, and 100 are really large. 0, 1, and 2 are really small. And none of the others are any larger or smaller than that. And then there's the middle. So if you think about what would that density distribution look like, there'd be a little lump here and a little lump there, nothing except for one point in the middle, right? So that looks pretty big. What's this? So I'm willing to go with that. How about the smallest one? Yes?
2.
Oh, 2. Why 2?
Because all the numbers are lumped around the mean.
So if we were to instead look at the distribution or the density of this one, there'd be a lump all around the middle, around 50, and then there'd be 1 point at 0 and 1 point at 100. And why isn't it number 1? Because they're all evenly spread out, and so that's got to be where they're further away. You've got many more that are further away than the number 2, but they're not as far away as number 3. Good. All right, next one. Suppose the education level of the mothers in the Kaiser study is measured in number of years of schooling completed. So rather than being a factor, it's number of years of schooling completed. The SD for the education level of mothers in the study, age 25 and over, is around which of the following values? So this is about the SD. Okay, you've had your half minute. Tell me one you're sure it's not. 3 pounds, why not? Units, right. 5 inches, it's not. The units are wrong. So we've narrowed it down to 1, 4, or 9. So the SD says roughly how far away is a typical value from the mean. So could it be 9 years? What do you think a typical value is? Anywhere from like 12 to 16? And if it were 9 away, you'd be going up to like, 20-something, and you'd be going down to, right, or 7 or something. And that doesn't seem like, that seems a little big. Whereas 1, what if it were 1? The average were 14, that would be saying most everybody's between 13 and 15. That doesn't seem right either. So sometimes we do these by a little bit of process of elimination, and 4 seems like a good answer. Next one. The governor proposes to give all state employees a flat raise of $70 a month. In these times, you can tell that this question was not written in these times. What would this do to the average monthly salary of all state employees? What would it do to the SD? What if the proposal were a 5% increase? What would this do to the average monthly salary? What would it do to the SD? You should care about this question because this is going to affect you when you go into the workplace. Whether there are percent increases or flat increases. Time's up. All right. What does the $70 flat do to the mean? Yes?
Nothing, because like it's like constant. Like,
Well, it doesn't do nothing.
I mean,
Well, if it does, I'll take your increase.
it increases, but I mean.
It increases it to the mean.
Yeah.
Two questions are there. First, what does it do to the average monthly salary? And what does it do to the SD? So I'll take your answer for the SD. Yes? The SD is nothing. Yes, it's a shift of $70, so it doesn't change the shape. Yes? The mean would go up by 70. That's right. So the average goes up by $70, and the spread about it doesn't change. What about the 5% increase? What does the 5% increase do? You answered already. Somebody else. Yes. 1 point what? 1.05. So doing a 5% increase is like multiplying everyone's income by 1.05. And so that would increase the mean by 1.05. And what does it do by a factor of 1.05? And what does it do to the SD? It's same, right? Is that what you were going to say? Yes, it multiplies the SD by 1.05. So that means it stretches out the distribution. So those that were making more are further away from those who are making less, right? A 5% increase if you are only making $1,000 a month is smaller than a 5% increase if you're making $10,000 a month. Yes? Because that gives it, the new value will be 5% higher than the existing value. So think of $100, multiplying that by 1.05 gives you $105, which includes the 5% increase. Okay, skin fold thickness is used to measure body fat. Here's a density plot of skin fold thickness. The units are in millimeters. The 20th percentile is blank 25 millimeters. Fill in the blank, or can this not be determined? Is it quite a bit smaller than 25 millimeters? Around 25 millimeters? Quite a bit bigger than 25 millimeters. The 25th percentile. Yes, you ready to answer? Quite a bit smaller? Yes, why? Right there, right about there's, big. Yeah, got that one before the time was up. Yes, if we look at 25 and look at the area under the curve to the left of 25 millimeters, it's a lot. It looks like it could be more than, that could be the median or even larger than the median. Good. I think this is, we might have one or two more questions. A density curve is shown below. Is the interquartile range around 25 or 15, 25, or 50? Let's do this one together. Where's the center? 50. Interquartile range says that that's the chunk. So this is very symmetric, which is nice. So if it's very symmetric, then we can sort of take the 50, take the possible IQRs and divide them in half. So the 50 says, okay, is there roughly half of the people are between plus and minus 25 of 50, which would go 25 to 75. The other one says, is it roughly within 12 and a half of 50, so 38 to 62. And the other one, is it roughly between, 43 and 57? What do you think? Can you rule one of them out right away? Any? What do you want to rule out? Oh, I didn't know 50. Good. I'd rule that one out. And now we're down to 15 to 25. What do you think? It's 25. It's a little hard, I think, to see this. You need to say, okay, from about 38 to 62 or so, is that half? And I think it is half. One more question, or there's two more, but let's look at this one. You're looking at a computer printout of 100 test scores, which have been converted to standard units. Glancing at the first 10 entries you see, minus 6.2, 3.5, 1.2, minus 0.13, 4.3, blah, blah, blah. Is there anything wrong? Yeah? That's okay. It's true that some have 2 and others don't, but think of it as 6.20. I don't think that's not a main issue. Yes? Yeah? Why do you think they seem too big? You're assuming it's normal. But you don't even need to assume it's normal to answer this question. But you're on the exact right track. They are too big. But why? Yes? That's right. Standard deviation should be 1 in standard units. And these numbers are so big, 11, 6, 6, minus 6, 4, that it's hard to believe that the standard deviation of these numbers is going to be around 1. That's right. Last one. An investigator has an electronic file showing family incomes for 1,000 subjects in a certain study. These range from $5,800 a year to $98,600 a year. By accident, the highest income in the file gets changed to $986,000. Does this change the mean? If so, by how much? Does this change the median? If so, by how much? I think the second question's easier. The second part's easier to answer. Does it change the median? No, because if we think of the distribution, no matter what shape it's in, if it's a long right tail, we're just taking the biggest value and shoving it way up to 986,000. That's not changing where half of the middle of the distribution is. So it does not change the median. Does it change the mean? Yes, by about how much? You can actually get a better estimate than a lot. You can. Yes?
887.
Now that's an exact answer. Very good. 800. I assume you've done your math correctly. 887.4. How would we do it? Just order roughly. Yes.
98, well, you need to figure out what the difference would be.
How much extra has been added on? That's right.
About
100,000.
About 90,000.
No, we've added about.
About 900,000.
That's right.
And then you divide that by 1,000.
That's right. So we've added a lot on roughly 900,000 and to that largest observation, and we're dividing by 1,000 because that's the total number of numbers in our list, and therefore we get about 900. In fact, we haven't added exactly 900,000. We've added, I guess, 887,400 or something. Okay. All right. Correlation. There's 2 remaining concepts that we're going to talk about today. Correlation we introduced on Wednesday, and I said I'd give you the formula for it today, and here it is. The correlation coefficient is how we measure linear association between 2 variables. To do that, we need to have pairs of measurements. We do have pairs of measurements for the mother's and the father's height. So we've got these couples that have a baby. We've got the mother's height, the father's height. What we do is we convert the mother's height to standard units. We convert the father's height to standard units. Then we take the average of the product of those. Now, R does this for you automatically, but it helps to know what the basic computation's about because it gives you an idea as to how to think about the correlation coefficient. So if we see this, we see we're looking at, we now know that the X's are now in standard units and the Y's are in standard units. But if we think here, the X's are the mother's height. And when the mother's height is above average, xi minus x bar over the SD of x will be positive. And when the father's height is above average, it will be positive. And so we're multiplying two positive numbers together. When the mother's height's below average, if the father's height's below average, we're multiplying two negative numbers together, which also turns into a positive. So if there's a positive linear association that says above average heights of mothers tend to be associated with above average heights of fathers, and below average heights of mothers tend to be associated with below average heights of fathers, that's going to give us a positive correlation coefficient. Okay? On the flip side, if the taller women married men who were below average in height, not just shorter than them, but shorter than the average male height, and shorter, and the other way around, that would give us a negative correlation coefficient. So properties are, correlation coefficients always between -1 and +1. If you saw a series of scatter plots that have the same SD, but the correlation coefficient is increasing, as it gets closer to either +1 or -1, the points are clustering more and more tightly around a line. That line is the SD line, and it has a slope, which is the SD of y over the SD of x when the correlation coefficient is positive, and it's minus the SD of y over the SD of x when it's negative. If it's exactly 1 or -1, then all the points fall exactly on a line. Remember, we've converted the x's and the y's to standard units, so also the correlation coefficient is unitless. So any kind of linear transformation of our data doesn't change our correlation coefficient. And it's symmetric. If we compute the correlation between mother's heights and father's heights, that's going to be the same as the correlation between father's heights and mother's heights. So here's the actual data for our particular groups of mothers and fathers. We've already seen the average height of 64 with an SD of 2.5 for the mothers. For the fathers, the average height is 70.2 and the SD is 2.9. And if you remember, I have not replotted that sort of big blobby looking scatter plot, which showed that there wasn't a really tight correlation. But there is a positive linear correlation, and that is 0.34 for the heights of mothers and fathers. Other questions on that? And I'm about to do something really quite different for the last 7 minutes of lecture. Questions? No? All right. So I'm going to introduce sort of the last plot of this unit of graphics, and they're really cool plots, and you can read about it. You might have already read about it in the infants. If you read the full section on the babies and smoking in the reader, you will have come across this plot already, but you might not have really looked at it that closely. Lots of times we want to compare two groups in terms of knowing what their distributions do. They have this roughly the same shape. So only shape, not are they exactly centered at the same place, or do they have the exact same SD? So we know mothers and fathers have different means and different SDs, but the question might be, are their distributions the same shape? These data do not have to be paired. It could be any set. It could be two different subsets, like the birth weight of the babies whose mothers smoked and the birth weight of the babies whose mothers did not smoke. They're not paired in any way. They're two separate groups. So far, all we've been doing is plotting density plots and either juxtaposing them or superposing them. And what I'm going to show you today is what's called a quantile-quantile plot. And so that's getting at, it's using quantiles, and that's where our pairs are coming from. So essentially, we compute a slew of quantiles. Here's just a handful of them, ones that we can easily kind of latch onto. 10, 25, 50, 75, 90, or 0.1, 0.25, depending on if you're using percent or proportion. So the 10th percentile for women, or the mother's quantile for 0.1, is 61, and the father's is 66. The 25th is 62 and 68. The median is 64 for women, 71 for men. The 75th upper quartile is 66 for women, 72 for men. I'm getting pairs out of this by matching up the quantiles or percentiles. So now I've got pairs. And what I do is I make a scatter plot of those pairs. So I'm comparing the two distributions by looking at a scatter plot of the pairs of quantiles. There it is. I've jittered it, because you know why I've jittered it. Now, if these quantiles fall on a straight line, that says that the two distributions have the same shape. So if it's roughly on a straight line, then the two distributions have the same shape. So this is roughly on a straight line. We've got some really tiny values over there, which show that the women have, there are a few women who have unusually small heights compared to the, so that gives you not really a tail, but more, I'd say more outliers. So here's an idea to give you, so the last two plots are just a way for you to see what a quantile plot gives you. So I have idealized density plots and then the quantile plot associated with them. The one on the left looks nice and normal, symmetric. The next one in the middle is a density plot that has a long right tail. And so if I plot the quantiles, where on the x-axis are the quantiles of the normal-looking one, and on the y-axis are the quantiles of the one with a long right tail, you see that it curves upward. So that says that when we're comparing these two distributions, the one on the y-axis has a longer tail, longer right tail than the one on the x-axis. In the book and the chapter on the infant health, there's a whole slew of these that sort of show you what they mean, what the different shapes mean. The last one I'm going to show you is this one. Again, we've got a nice sort of normal bell-shaped curve. The one in the middle is also bell-shaped, but its tails are longer. And on the right, the far right, we've plotted the quantiles. We've paired up the quantiles for these two distributions. We've put the quantiles of the normal on the bottom and the quantiles of the one with the long tails on the vertical axis. And you see that it is mostly a straight line, but then it curves up, saying that I've got a long right tail, and it curves down, saying I have a long left tail. So you can, it becomes a bit of an art, but you can learn how to read these quantile plots, and they can tell you a lot about a distribution that's much harder to see when you're just looking at the density plots. All right. That's it for today. As an extra treat for you all, if you would like to come and visit me today at lunchtime, I'll be in my office at noon if you've got some questions about your data and how to get your data into R, or how to find extra data or make a particularly pretty plot. From 12 to 1, I'll be in my office if you want to stop by.